is two things. Number one, I'm going to go over this chapter. Then I'm going to go over Article 408 in any secret book that talk about panel boards and summarize the major things that relate to you. So when we talk about panel boards, if you guys remember, I'm going to summarize very quick, what you need to know. When we did residential, we had panel boards start with very simple, something called load center. Do you guys remember that? Now load center, drop that baby. This is usually 100 amp to 200 amp single phase systems. Now drop that one. So that's the first cheapest piece of equipment you can buy is a load center. You drop that one in your basement. Do you guys remember that? That's a load center. We don't think about it in a commercial, though you can install it. So mostly single phase, though you can come as a 3-phase too. The second one is panel board, the one that we're talking about right now. These guys, you can get them from 100 amp all the way to 1200 amp for the most part. To 100 amp all the way to 1200 amp, any voltage that you can imagine. I'm going to go to 208, 480 for the most part, 240 for the most part, and also 3-phase. These are 3-phase systems. The difference between, if you guys remember what Todd Christensen said about the difference between panel boards and load center is one major thing. Panel boards for the same amp, bigger, fatter, have more gutters, space for you to pull the wires, space for you to pull the wires. They come in 3 pieces. One is the box, right? The first thing comes as a box, and then the chassis inside the box, that one that has all the bars, the cover bars. Yeah, you mount the chassis inside the box, and the third piece is the cover for the whole panel. First is a box, just an empty box, if you can imagine now. The second one is the chassis. These are the phase A, phase B, phase C, the neutral, the ground. You mount this one inside the box with the circuit breakers, and then to make it safe, you put a cover around it and a door, a cover and a door. So that's what you're looking at. So this is the inside here is what they call it. Here's the chassis. That's my chassis. The box is the outside right here. And what else? Then you need the cover and you need the door. Where's the cover? The cover is right here, including, of course, the door. 3 different distinct pieces that you can ship them differently. Cool? You can get them from 100 amp all the way to 1200 amp. The third piece of equipment that you can install is called switchboards. This one, gosh, it started making sense. Switchboard at probably 1000 amp all the way to 4000 amp. And the last piece is the most expensive is switchgear. This is also start making sense from 1000 amp to 4000 amp. The difference, Chris, do you remember how Todd said the difference between switchgear and switchboard is what? Switchgear and switchboard, guys, they are standalone. I can put it right here in front of you, standalone in the middle of the room. Right? Its structure is different. It can stand alone by itself. Panel board, you have to lay it against a wall. They have to be panel boards, and the first 1 and 2, they have to be in a wall or on a wall. They have to be supported by something. Okay, when you get into the switchboard, they sit right in the front, in the middle of the room. The difference between switchboard and switchgear. Switchgear is the top notch that you can buy. Most of switchgears are drought switchgears. They're rated for, we'll talk about this one when we do coordination. They're rated for 30 cycles, means coordination is great. So I want you to think of them in terms of expense. The higher the number, the more expensive the equipment. Okay, and the bigger the equipment, more expensive, the bigger the equipment. All these are covered in Article 408 in the NEC code. Article 408 covers all of these babies, all these types, and it doesn't distinguish between, for the most part, between any one of them. Any question, guys, about these? What we're using in our project, the project that you're using, it's going to be a 4000 amp switchgear, and mark your word, we're going to be using an ANSI switchgear. So this is the design that we're using for our project. We're using the main panel is going to be a 4000 amp switchgear. The sub panels are going to be a switchboard. Most of the sub panels that we're using are going to be actually right here. All the lighting panel, receptacle panel, equipment panel are going to be switchboards. So we're using, I'm sorry, panelboards. Panelboards. So most of the, so just to give you an idea. So we have receptacle panel, we have lighting panel, mechanical panel 1, mechanical panel 2. They're all going to be right in here, and emergency panel. The main switch gear, main switch panel or switch gear, main switch gear, it's going to be right in under the switch gear. Any question, how is this related to the project that we're doing? We're not using a switchboard in this project. Now, what is a switchboard? The switchboard is a cheap product that can give you some advantages of a switchgear. Any question? The most important thing to understand is the difference between switchgear, switchboard. They stand alone. They sit right by themselves, big towers. When you go to switchgear, I think it's like 62 inches deep, the depth, and 92 inches high. And the length is as many as you want. They're sections. We'll talk about this one. I'll let Jim Rasmussen talk about it, about switch gears as we go through. Any question, guys, about this? So that's what I wanted to talk about in terms of panels. Just summarize what we have done in the winter. Connections, these are lugs, guys. The code says you cannot put 2 conductors under 1 lug unless the lug is rated for it. So as you go through, you're going to have that this is lug, for example, is rated for multiple connection. If you're paneling 2 conductors, this talks about the lugs. So this is my panel, and I'm bringing and bolting it lugs only, and I'm bringing 500 kcm here and another 500 kcm here. This is how you bring 2 feeders, and this is phase A. Let's just say this is phase A. Can you imagine B and C the same, right? So that's a way where you can tie multiple feeders into 2 different lugs in the panel. What the code does not allow you, Tom, my friend, is to bring 3 feeders under 1 lug. It's not rated for it. 1 feeder per lug. 1 feeder per lug, unless the lug is rated for it like this. Anyway, so this is for the most part for the type of the installation that we use. We don't get into sizing the lugs for the most part. Circuit breakers that you can put in the panels, up to switchboards, guys. For the most part, if you have a switchboard and lower, like load center and switchboards, load center and panel boards. Load center and panel boards up to 1200 amp. You could have single pole circuit breakers. You could have 2 pole circuit breakers, or you can have 3 pole circuit breakers. You guys know the difference? So this single circuit breaker, I can bring my power in, and this is my, let's see, it's coming from phase A. It's going to my lights here, and I need a neutral. So a neutral bar will be sitting right here. Here's my neutral, and come directly into that one. Single pole circuit breaker. The voltage could be 120, could be 277. The most, you guys are going to be using 2 circuit breakers types. One is going to be rated for 120. The other one is going to be rated for 277. Line to neutral. Okay. So here's single pole. If you go, this is installed in panel boards. All types of panel boards. The 2 pole. Where would you do 2 pole? Because they're very familiar. If you have a load that says 208. 240 or 480. All of them are single phase. This is where you can tie a 2-pole circuit breaker. So this is phase A, phase B. This is a load machine that runs at single phase, but not 120. Single phase 208, 240, or 480. That's where you use a system like this. A good example of this one in dwellings is air conditioning and so forth. Not a whole lot of equipment that run at 2 phases. Most of the equipment either are single phase or 3 phase. So this is the last equipment that you guys are dealing with. You're going to have phase A, phase B, phase C, and here's my air handling unit, right? And this is, let's just say this is 600 amp, and the voltage is 480, and of course it's 3 phase. 480 3 phase, and here's phase A, phase B, phase C. A, B, and C. Make sense? So in a panel board, you can put any of these, single pole, 2-pole, or 3-pole circuit breakers. Most of the time, you are either single pole or 3-pole. Most of the time, you are either single pole or 3-pole. Circuit breakers or fuses, no problem. You can put fuses or circuit breakers. Here's another example of 100 amp 3-phase. This is a a picture, guys, of a fused switchboard or a panel board. This could be 1200 amp. Let's say 1200 amp. The main is here is 1200 amp fuse with a disconnect, and each one of these usually, Chris, rule of thumb, the largest feeder that you can feed from a panel, rule of thumb, without getting into problem with coordination, is half of the main. What's half of the main? 1200. What's half of 1200? 600. So the largest would be 600 amp. Now, can I feed 1000 amp from this piece? Yes, but it would be kind of foolish. If you have a load 1000 amp, might as well feed it from a switchgear direct. So this would be, say, 4600 amp. This is, say, 400 amp. This is 300 amp. This is 200 amp. This one, let's just say 100 amp. And on this side, I'm going to use 60 amp, 80 amp, and give me another 90 amp. Give me another one, 125 amp. And this one, let's just say 350. 350 is the size. Here's a panel full of fuse circuit disconnects with a main. Your options are either circuit breakers or fuses. Which one is better? Both of them are good. A lot of people like this circuit breakers because you can reset them. A lot of people like fuses because fuses, you know if they work or they don't. If they work, they burn. You replace them, you're guaranteed they work. Circuit breakers, you reset them. Every time you have a short circuit in a circuit breaker, technically, if it's a high voltage, you have to retest the circuit breaker to make sure nothing have the characteristics of that circuit breaker have not changed. So I like circuit breakers. I'm an engineer, but I can see the point where people like fuses, because the fuse, if you have a short circuit, they blow up, you throw them, you put new ones, you know it's ready for another fight. A circuit breaker, it trips, it's supposed to be ready for another fight. There's one little problem, and we're not talking about just a 15 amp circuit breaker here. We're talking about a 1000 amp circuit breaker. We're talking about big stuff. 600 amp circuit breaker. You have a short circuit, a 600 amp feeder, that's a substantial amount of energy when right through the circuit breaker. Now, would the circuit breaker magnetic, thermomagnetic characteristics altered because of that short circuit? A lot of people say yes. You're supposed, if it's a voltage 3-phase, you're supposed to pick it up, go test it, make sure it works. So,
with most fuses, do you have to recalibrate those, or are they just good until they're dead?
Good until dead. You have to, other than the connections, make sure it's not loose. They're good to go. Most of the fuses. There's adjustable circuit fuses. Yes, that's exactly what the calibration for the breakers need to calibrate it, especially after a short circuit. So here's my panel. In the project that you have, guys, Nick, my friend, if you look right here, if you guys remember, here's the bus coming here and feeding transformers. It's a 480, feeding transformers 208 all around it. Each one of these transformers is feeding panels. Like this transformer here is feeding panel 4, 5, and 6. And if you come here, it's the panels are located. Here's panel 8. So these, all the panels are located. Here's panel 8 here. And this is panel 14. Here's panel 9, panel 10. So all the panels in this project are located right here. If you look at this side, all these panels. So when they talk about the system that we have, all these panels 1 through 15, they're giving you all the amps in these panels. I can't read, you can't read. So we have the amps, breaker ratings that they have, and the main amps. The most important thing is these, the main amps. So you can see all the main amps for these in the building. So who cares? These are all the panels that are installed in this industrial project. They are located right here around the perimeter of the building and right in here, numbered. And they are fed from, if you guys can see a transformer right here, there's a transformer that's feeding, for example, P4, 5, and 6 coming from one transformer. There's another transformer feeding P15. There's another transformer that's feeding 7 and 8. This one is feeding 11, 12, 13. This one is feeding P14. So all the panels are fed directly from the the feeder busway that we're talking about, and they're placed around the perimeter. They're using them to feed receptacles, mechanical equipment as heating, cooling systems, and they're using it to feed lights. All these panels are dedicated for mechanical equipment, lights, and so forth. Anyway, so this is all all the feeders, all the panels that's in this project. You can see the first one in the basement, for example. I have P1, location basement north corridor. It's a breaker 100 amp, it's 28120. Number of circuit breakers is 19, 20 amp single pole, 2 20 amp two pole, and 5 20 amp single pole, and lighting and receptacles, all of them. Can you guys see? This is the panel schedule basically for this project, the panel schedule for this project. If you guys look at P5, manufacturing breaker, it's feeding lighting and receptacles, and there's 5 receptacles, 50 amps, and so forth. And by the way, these are the ones that are feeding the plug-in busways. Look at the last one, P15, right here. It's feeding the chiller. Can you guys see that? 175 feeding the chiller. Anyway, so this is all the panels, 15 of them in this manufacturing floor. 15 panels in this manufacturing floor. For us, we're going to have probably end up with 5 panels or so in our project. So that's a panel schedule. It gives you the panel name, the location, the main breaker, the voltage, the number of circuit breakers of every amps and every pole, and what's this panel is for. Any comments, guys, about this? We're describing the project that we have. Okay, now if you guys remember when Todd was here, you can tab a feeder to feed multiple equipments. So what they're taking a feeder here, okay, and from this feeder they're tapping it to feed, I can't remember, say this is 100 amp, and they're coming from here and continue to another, and this is so this is sub feed. Can you guys see in, out? It doesn't go through a circuit breaker. So let's just say this is 300 amp. I know probably I should. So it's 300 amp, and you continue to the second panel. This is one way of doing it. What's the alternative? The alternative is to bring a feeder from here to the switch gear, if you have a switch gear. But if you look right here, right in here, it has 150 amp feeding panel 4, 5, and 6, right? So what they guys did, they took a feeder, 150 amp, and they fed 4, 5, and 6, exactly what you're looking. With a feeder, junction box, tab, up. All these tabs are made in a junction box or in a gutter, in a junction box on a gutter. There is a distance that you have to be, and remember that 10 foot, most of the time you use the 10-foot tab rule between these, 10-foot tab rule. When you say a 10-foot tab rule, guys, the conductor that you can tab here, one of the rules based on the 10-foot cannot be smaller than the main 1/10 of the main. 1/10 of the main. So that's what the rule that they're using, because some of you say, well, Chad, this conductor is smaller than this. Where's the overcome protection device for this? That's they go by the tab rules, the 10-foot and the 25 feet rule. If you can tab a conductor from another conductor up to 10 feet. The condition is at the end you have to have a circuit breaker that protects the conductor at their amps. You can't go more than 10 feet. You have to protect them from physical damage with a conduit, like you can see. And the main, in this case, suppose the overcome protection device here, that cannot be more than 1,000. Here's 1,000. If this is 1,000 amp, what's 1/10 of 1,000? 100. So these conductors have to be rated for 100 amp each. The conductor rated for 100 amp, 10 foot, we're good to go. When you guys do industrial, tabs becomes a big deal. I have a lot of examples about tabs calculation. We're going through it. But this is how they do them, that tab rules. Because if the conductors here is 1,000 amp worth of conductors, you can't just take a 100 amp worth of conductor without the overcome protection device right here. If you remember the plug-in busways, where did they put the overcome protection device? They put it right in here. As you take the amps, you put the overcome protection device. Sub-feed and feed-through, what you're looking at here is sub-feed. And remember, Todd talked about this when they went to sub-feed. Feed-through is you go in, you go out from this side. They're not using feed-through here. They're only using sub-feed. Either a tab or a sub-feed, in and out. So if this is 300 amp, then this has to be also, the cable coming out has to be 300 amp. And I know it doesn't correlate with what I put there, but any question, guys, about the tabs? We'll talk about calculating the tabs. It's coming. So don't sweat it too hard. but just tell you how they did this project. They're using a fuse disconnect, guys. Here's a typical fuse disconnect, lugs only panel. If you guys, I know you know that one. This panel, the way it looks right now, it's main lugs only, or main circuit breaker. You guys remember that? When you were looking at Revit, it was talking about panels at MLO, main lugs only, and MCB, main circuit breaker. Looking at this, where's my circuit breaker here? Do I have a circuit breaker here? No, this is what you're looking at is an MLO, main lugs only. What you're looking at is, because we have a fuse, these, they call the fuse disconnect, what you're looking at is a fused disconnect panel board. Cheaper, bulkier though, bigger than a circuit breaker panel board. For the same size, the fused disconnect panel board will be bigger, physically bigger than the circuit breaker size. But a lot of people like him, like I said, Chris, because that baby fuse, if it trips, it will trip. You know it trips. If you have a short circuit, you know it works because it opens, and you have to install a new circuit breaker there. I don't know if you guys can see that these are three-phase, and three-phase. There is nothing called three-phase fuse, guys. They don't make a three-phase fuse. Fuses are single-phase, but the time, can you guys see the fuses just in one phase, in one phase, in one phase. But to isolate them all together, what do? You have to have a disconnect. That disconnect, and that's why every time we talk a fuse, we talk disconnect.
So if one blows, it will take the other two with them?
No, not necessarily. Not necessarily. Not necessarily. So if I have an air handling unit here, and I have a ground fault, this is air handling unit, and I have a short circuit on phase A. Let's just say phase A grounded. I can blow up this fuse. Now the air handling unit will continue to run, but guess what? The others, I think, I can't remember, it's 150% more amps is going to be going in. So when the air handling over current protection, the air handling unit over current protection device see 150 amps, 150% more amps coming into it, it will recognize that there's a short circuit and will trip and overload. That's how we protect it. Yeah, you can single phase. That's called a single phasing. One disadvantage of fuse is single phasing. But if you have machines, you have an overload, the overload will see when you lose a fuse, the other two phases will be overloaded with current momentarily. And the overload will see the overcurrent on the second two phases and will trip on overload.
That's enough motor starter.
That's exactly part of the motor starter. VFDs has protection from single phasing, a lot of protection, they call it single phasing. Any question, guys, about this fuse disconnect? For our project, guys, we're using circuit breakers, not fuse disconnect, circuit breakers. Okay, this is just a feeder, an example of feeder busway, cable tab busway, primary fuse switches, just a whole system put together. What I want to emphasize, because we were talking about the busways, I don't know if you guys can see that tab over here. Number B is a cable tab box. So we tabbed the busway. This is my busway coming in. I tabbed it. Then, if you guys can see that, the second thing I need to do is a disconnect. And instead of putting the disconnect here, they just grabbed it down based on the tab rule. Less than 10, I can do that. Less than 10 feet or 25 feet, I can drop it down a little bit. So they put the disconnect here. That will be my C, right? And then they brought it to D is my transformer. They fit a transformer here. And then out of my transformer, I went to H, which was my secondary feeder protection, right here, overcurrent protection device, basically. These are overcurrent protection device, primary, secondary for the transformers. And then out of there, we went to E, which is a power panel. So we fit, can you guys see that? Fit the power panel out of it. And so we fit the power panel. They're using a wireway. Then they took a couple of wireway out of this panel to feed F, which is, what does F do for a living? F is motor controllers. So we're feeding all these motor controllers. And G is conduit to motors. These conduits are not coming. These are going up, guys. They're not going through these are going to motors. They're not part of the bus. They're shown, right now it's confusing because it looks like they're going right through the busway. These are behind the busway going to motors. And these are also going all the way different directions. Anyway, so the key point is, this is typical for industrial. You have a busway coming in, you tab it, you put a disconnect, feed a transformer. Out of the transformer, you have a secondary protection. Then you feed a panel. Then this will be a lugs only panel, right? Why do I need a circuit breaker? Lugs only panel. From this panel, I feed multiple machines. That's what they did in this project. Any question? Later on, Chris, what they do, the better design than this is, well, we have to, the better design for this is to grab the feeder directly from here and put it in so-called MCC, Motor Control Center. So can you guys see all this junk here? All this junk, I can drop it directly into a box. And this box is called MCC, Motor Control Center. The driver, the starter, the disconnect, the overload, all dropped inside a box. That's called MCC. You still need the transformer though, because the voltage is different. If the voltage, this must have been 480 here, and this panel is 208. If the panel is 480, do I need even a transformer? I don't need a transformer. I can't emphasize, this picture is very, very important, guys. If you're to do commercial, industrial, very, very good application. What's the difference between using MCC and using what they're doing? This is much cheaper design, right here. What you're looking at, much cheaper design than MCC. MCC is expensive piece of equipment. This is where you can get into twice as expensive. So if this panel, let's just say this panel, for the heck of it, was, let's just say 600 amp panel, and I need to buy a 600 amp MCC, now you got yourself into double or triple the amount of dollar for the same MCC versus a panel board. Because MCC have pockets and you pull them in and out. They have the starter as well as the overcome protection device and a disconnect all in one. Clean though, nicer, cleaner design. Yes, sir?
Does it ever come across the safety issue where they have to go and
Do it here.
Yeah.
Safety, not a big deal. Reliability, yes. If the system is, from a reliability point of view, having all this junk inside an MCC, it's more reliable. Why? Because say if this controller is crap on you, right now I have to go disconnect the system. It takes me, a good electrician, it will take you half an hour probably to put the whole system. You have to lock out, tag out, de-energize and all stuff, and go change this controller. If it was a bucket right here, and it craps on you, you know what you do? You pull it out. Most of the time you have another spare one sitting. You might have to change a fuse or something on it, and you go and you pull it in, and literally within 10 minutes you're up and running. So if you have a load that's reliability is a big deal. A good example of this, guys, wastewater treatment plants. You can't just sit the pump that's pumping all the sludge. You can't sit it for 2 hours or an hour to go change something. They use a lot of MCC on them. Hospitals, sport arenas, all these places where you cannot afford to lose. If you have an accident, you can't have half an hour to work with it. You need to plug it in within 10 seconds, 10 minutes or 15 minutes, and MCC becomes a big deal. Any question, guys? And I will let Jim, when he comes, guys, talk a lot. He's an expert in MCC too. Nick? So that's how they did the system. I can't emphasize, guys, the book is very small and nice, but the information in it, I believe, in my humble opinion, is really nice. Very nice. Here's the panels. We talked about the lugs. So this is basically what we have. Let me go to see if we forget anything in terms of I like to do, as you guys probably noticed, that I like to do the pictures first. Identify panels, circuit breakers. So if somebody's to ask you, why do we need panels? Panels have two main functions: distribute the power to different branch circuits and protect this power, right? You have a circuit breaker. That circuit breaker trips up in short circuit and also branch out to feed different equipments. So that's basically the main building. We talked about this one. Lighting and small appliances. It used to be lighting and small appliances. They got rid of it in 2011, guys. Right now, what they're saying, lighting and appliances, panels. I'll walk you through 408. So it's really, for the most part, no difference right now. Here's what I want you to pay attention to. If you have a circuit breaker, guys, the circuit breakers are rated at 80%. So take this. If I have 225 amp panel, if I have a 225 amp circuit breaker protecting a panel continuously, I only can take 80% out of that. So Chris, could you please take 80% out of 225 and see how much load I can pull out of this baby here? 180 amps. Do you guys remember how when we were sizing panels, why we multiply the continuous load by 1.25? Remember that? We up it because as we size the panel, we're upping the panel so we don't get into a situation where I think my panel is 225 amp, but continuously it actually cannot carry more than 180. The way I do it, I start with the load. Multiply continuous load by 1.25, non-continuous load by 100%, right? No, add them all up, and then size your panel. If you do it this way, you don't have a problem with 80% derating on the panel. So see why we always do the 1.25 for continuous load, because of that one. We talked about the different sizes, guys, that you can buy a panel from. You can have the main lugs only or main circuit breakers, right? We talked about capping rules, protective devices, circuit breakers. So the protective device, guys, for panels, a lot of you know by now, is if I have a panel here and my panel is 225 amp, right? I can put my circuit breaker right in here, or I can put my circuit breaker right out here, right? But it would be a fool to put them in two different locations. So I can put my 225 amp panel. If I want to put it right here, so what do I do with this circuit breaker? It becomes main lugs only. This is main lugs only. Or I can put it right in here, and this becomes main circuit breaker. Everybody knows the difference between main lugs only, main circuit breaker panel. You guys have been sizing with me. There are two sizes for panels. The size of the actual copper here, 225 amp. Smart engineers, they match the size of the copper to the size of the overcome protection device. But I can put 100 amp here. If I know my load is 100 or less, I can have the copper 225 amp panel, but the overcome protection device ahead of it is less than what it's rated for. That's okay. Because the overcome protection device, by code, Ashley, the size of the panel is the size of the overcurrent protection device that protect the panel. So, William, if I ask you, what size is this panel here? It's a 100 amp panel. What size is this panel?
225.
Thank you. Even though both of them are 225, but by code, the size of the panel is the size of the overcurrent protection device that protects it. So I have 225 amp panel here and 225 amp panel here. I protect the first one with 225 as I should. Engineering wise, that's the best way to do it. Right here, I know my load is really smaller than 225, and I had a good deal at 225 amp panel, so I bought it. But I don't want to pull a 225 amp cable, right? So I go and put a 100 amp break at 100 amp. Then in a case like this, you have to then your panel is a 100 amp panel, if that makes sense. Overcome protection device, guys, you're familiar with what they do. Why do we have them? They protect you over circuit breakers or fuses. Overcome protection device. So they protect you from overload. So provide a proper overload protection. That's short circuit as in this case an overload. They have to provide also short circuit protection. Interrupting rating. Remember how we talked about the interrupting rating? Suitable voltage. You have to be suitable voltage, and you have to do overcurrent protection coordination later on. So when I say a circuit breaker like here, I'm going to have, this is 100 amp circuit breaker. It's 3-phase. The voltage is 480 volt, and the interrupting rating is 35,000 amp. What else are we missing here? So this is how you buy a circuit breaker. You buy it by the actual size, then how many phases, 3-phase, 3-pole, and what's the voltage that's rated for 480 or 600, and what's the interrupting rating, 55. This means right in here, when I tie it to a panel, this panel have to be at least 100 amp, and the voltage 480 volts has to match it, right? And the interrupting rating at most 35 kilo amp. I can't go and make a short circuit right here that's higher than what the overcome protection device can handle, right? Otherwise, there's going to be big explosion. Very, very important when you talk about circuit breakers. These are very, and then we coordinate them with upstream. So if you have an upstream panel here feeding, right, and you come over here with a main, And let's look at that main here. That looks like a good main. So let's just say right here is 1,000 amp. So I want to make sure later on you guys want to do it with your friend Chad. These two circuit breakers have to coordinate with each other. If you have, in this case, I put the circuit breaker here. These two have to coordinate, meaning if I have a short circuit here or here or here, anywhere in this area, the one that should trip is that one here. And again, I'm gonna, to make it work, I'm gonna make my circuit breaker right at the top, and all this information is about that guy here. We will do an over-competition coordination, guys, meaning short circuit breaker downstream can be only cleaned by the short circuit breaker closer to it. Otherwise, you'll have nuisance tripping. When you have over-competition device, guys, the shorter settings, the better. I'll explain that one when we go. So if you have to set the circuit breaker at 35,000 or 25,000, which one is more protection? 25, the lower the better. So you'll remember that. Disconnect, talk about this one. Okay, so that's basically it in terms of circuit breakers. Next week, guys, as I said, Jim Rasmussen is going to be here. He will talk about GE's design of switchgear, switchboard, MCCs in details, from a manufacturer point of view. If I want to say one thing that's confusing for a lot of designers, the size of the panel is the size of the over-competition device that protect that panel, period. So let me be quick, guys, very quick. I know my time is approaching here. Take you to the article that talks about panels, very shy little article. 208. Did I say 408? It should be 408. Thank you. 408. So if you guys go to 408, it says switchboards and panels. Switchboard. It talks about the construction of the switchboards and the panels. Does not apply to equipment operate. The only restriction is it doesn't apply to anything higher than 600 volt. Support. You have to support the busways. It talks about all this support for busways and so forth. Same vertical section, other. Later on, guys, you're going to have something called horizontal bus and vertical bus. We'll talk about this one with the equipment. If you use it as a service equipment, you have to provide bonding between the neutral and the ground. That's another thing. In panels. Terminals, blah, 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 including grounded conductors for load equipment shall be located that is not necessarily to reach X. So this is just protection for manufacturer. Arrangement of the phases from right to left ABC, top to bottom ABC, front to back ABC phases, right? So that's what they're telling you. Switchboard, ungrounded system. If you have a panel that's ungrounded system, you have to mark the ungrounded system with the phase. High leg, remember that high leg panel? They tell you you have to mark it also with the voltage to ground between the high leg. Field identification, you have to identify, have a directory. Remember that directory, guys? That you have to have a panel schedule that you guys are doing. That's code requirement. 408.4a tells you have to have one. Sources of supply, in 2011, Ashley, they require you to label every panel with the source of supply for that panel. So I need to know what's the feed for this panel. That's new. Clearance for conductor entering the buses. Unused opening, you have to close it. So it talks a little bit here about the switchgear design, clearances from sealing and so forth. And of course, working around equipment, you have to follow the clearances, panel boards, back feed, and so forth. So this is don't want to make it all panel. So this is a few construction. Panel marking, mark with the voltage and the amps, and maximum number of overcome protection device. The only limitation, the maximum number of overcome protection device, guys, is if you have main lugs only, you have limitation of, and you don't have an overcome protection device, you have a limitation of 6 disconnect in the panel. 6 disconnect in the panel, in one panel. Otherwise, you have to have a main. Backfeed devices have to be identified. If it's in a damp and wet location, you have to identify it, and so forth. The panel have to be grounded. A grounded conductor terminal have to be brought to the service. So this is a few things that tells you, summarize. I know you guys know almost all of it because we install it. A lot of this stuff also apply to the manufacturers, how to build the system. Any question about panel boards and switchboards? I believe what we give you guys is what you need to run with it. So not a whole lot. The most important thing that the code require you is really the directory that lists every circuit breaker has to be identified. What is it going to be feeding? In 2011, they added the feeder for the panel have to identified. So if I have a panel right here on the, I have to say fed from panel number 15 in room number 25. Fed from. Of course, it has to be protected. All the buses have to be protected. That's for the manufacturers. If it's in a wet location, what do you expect if you have a panel in wet location? It has to be rated for wet location, right? Dry location, NEMA 1, NEMA 3R if it's outdoor. So that's typical for electrical equipment. If it's in a hazardous location, Ashley, class 1, div 1, it has to be explosion-proof equipment, blah, blah, blah. That's typical for all equipments, not just for panels. Okay, any question? If the panel is to be used as a service, it has to be listed as a service, meaning you have to have a means of bonding the neutral to the ground, only if it's a service. If it's not a service, what's a service panel? The service panel is the first panel that the service entrance conductor land in. They sit inside it. That's service panel. So that's basically my, oops, you don't want that one here, circuit breakers. Any question, guys, about panels? If you open Cutler Hammer catalog that I gave you, or Square D, you're going to find tons and tons and tons of different type of panels. The most important, a good designer, guys, will pick up the panel that matches the voltage that you need and matches the amp that you need. Not higher, not too much high, or not too much low. That's the best panel. In terms of voltage, you have to match it. Amp have to match it, or be slightly higher, but not too much high. And the interrupting rating have to match what you have, or slightly higher. What's wrong with having 1,000 amp panel feeding 100 amp load? There's nothing wrong in the code wise, other than it will be called stupid design, because you're buying 1,000 amp panel when you only need 100 amp panel. So always think of economically. It's, you know, if you can go lower on the amps to match the best design, optimum design, that's the word I'm looking for. The optimum design is to match the load that you have with slightly future expansion. When we size panels, guys, always start with the load. Always. The start point for panel sizing is the load. If you look at the calculation there, we have part of the calculation that we're going to be using as sizing panels. How to size panels. We have done it before. It's not the first time we size panels, but we will be sizing panels based on voltage and amps and interrupting rating. Any question for Chad? Chris, did we cover everything? Anything? Did we miss anything? I know you read the chapter. You probably read the chapter more than I did. Okay, what I would like to do, guys, I would like to eat today. Oops, that is a surprise. Did they owe you a lunch? Oh boy. Okay, after lunch, guys, 11 o'clock, I would like really to walk you through the low voltage. Is that okay? Tell my friend, is that too late? Shall we do that? 11 o'clock. You guys continue working. I'll show you a few things. We have used low voltage in Revit. It's not a new thing. So